In this lesson, we're going to continue building our source by adding the missing element, which is the velocity, and then we're going to create finally our particle simulation. But before we do any of that, let's talk a bit about what actually is a particle. So a particle is just a point. So if I just create an add and I create a point, let's hide everything. So that is a particle. Since a particle is just a point, it doesn't have any shape or size. Therefore, it can't collide with any other particles. So for example, if I make a sphere over here and I scatter some points, even though particles can collide with each other, they can't collide with other objects. Now, the advantage of this is that particles are extremely fast to simulate, and it's one of the best ways to get started with DOPs and understanding how simulations work. And one quick parenthesis before we continue. Since Houdini 16 or 16.5, I can't recall, Houdini introduced position-based dynamics, or PBD for short, and it uses the concept of grains. So there's, for example, a pop grain node, which it actually allows you to give it a size to every particle, and they can collide and stick with each other. But that's outside the scope of this course. As far as we're concerned, our particles can't collide with each other. For all our effects, we're going to be using exclusively particles. The idea is to simulate points which are very fast and then instance geometry onto these points. So let's talk about the simulation part. We know what a particle is, but what's the next step? So Houdini has a pop solver. And if we create a pop network, so that's going to be a .NET that's already configured to deal with particles, we have the bare structure of what a particle simulation is made of. The main important node here is the pop solver, which you can think of as the engine, which does all the physics calculation to determine where our particle is going to be on the next frame. The solver allows us to add things like forces, like wind and drag and friction and collision, for example, and is solving a differential equation to find out where the particle is going to be. There is a very important concept at play here, which is one of the main things that sets apart DOPs from subs, and that's the concept of feedback. So for example, I'm going to just change something very fast. I'm just going to add to inherit velocity, and I'm going to hit play. Let's remove our guide, and let's set this to emit all the points. Okay, so we have a very basic particle simulation. Now, what is this concept of feedback? So feedback involves using the result of the previous frame and feeding it back into the solver to calculate the next step. And again, feeding back that result into the solver to calculate the next step, and so on and so on. So I'm just going to reset our simulation, and you'll notice the blue line is now gone. That's our cache. So in order to calculate where our points are going to be in frame 996, we need to know where 995 is, and then the result of 996 is fed onto the next frame. So you can see the particles are kind of like progressing. And that's the concept of feedback. We're using the result of the simulation to drive the equation. So basically all the equations the pop solver is solving every frame, it's doing it based on the result of the previous frame. So this is the reason why you can't just go and say, for example, I'm at frame 1001, I want to know what frame 1032 looks like. If I click on it, it actually has to calculate all those frames to know what is happening. Let's make this a bit slower, just so you can see. I'm going to reset it again, and let's add, for example, 10 substeps. And now if I click frame 1032, well, this one is still fast. Let's try again. 1032. So you can see it's thinking. It has to calculate all these frames before it can calculate 1032. Basically, it needs to know where 1031 is, so it can calculate 1032. And it has to calculate 1030 to know where 31 is, and so on. So that's why simulations are slow. You actually need to calculate the whole frame range, even if you need just one frame. You can't start midway. So this pop solver is going to keep solving this forever and ever. So it'll keep going until whenever we tell it to stop. So let's have a look at what's actually happening here. We're going to go out and actually start using our own geometry. So we can delete this. And let's go back to the first frame. And I'm going to change this back to default, so they were back to 1 and 1. And here, I'm going to change this back to using inherit velocity. Okay, So let's have a look at the anatomy of a pop network. So we have a pop object. You won't really be doing much with this node. The only useful thing here is that you can set the physical parameters. So you can set the bounce, the friction, which we're going to set later on. Then we have the solver. In here again, the only thing you might change is just the substeps, as you saw before. So the substeps means, I just explained how every time we go to the next frame, the solver is calculating a certain equation to figure out where the particle is going to be. Substeps means solving that equation more times in between frames. So if I have, for example, 10 substeps here, that means that when it goes from frame 995 onto the next frame, it's going to run this algorithm 10 times. So it's going to be more precise. Basically, the more substeps you have, the more precise your simulation is, but also the slower it is. So let's go back to 1. And then we have over here, there's some collision behavior, but again, all these things like I never change. The only thing you'll ever be changing is the substeps. And now for the most important one is the pop source. So this is how we fit things into the pop solver. You can see in here, it says what's the source, and this is connected to it. So by default, we're telling it to emit all the points, and it's using the first context geometry, which means the first input of the dop network. And then in the birth, basically when you have an impulse activation set to 1, it means that every frame is going to be emitting. Finally, we have life expectancy over here. This is set in seconds. So in our case, since we don't want our particles to die, we can leave it at the default of 100. That means that they're going to keep existing throughout the whole simulation. And then attributes. So this is one of the most important ones. The pop solver recognizes certain attributes, and they actually have a meaning in these equations that it's solving. Arguably one of the most important ones is the velocity attribute. And the way the pop solver works is that it affects the position of the particles based on the velocity. This is because the first derivative of position is velocity. And based on the velocity, the pop solver can integrate or solve what the position will be. And we can go a step further and use a force attribute, which you can think of acceleration. The acceleration is the second derivative of position. So if you have a force, it will calculate the velocity, which will calculate the position. For this reason, I recommend either using force or velocity, but not setting values for both at the same time, unless you really have a reason and you know what you're doing. The whole idea is that you just provide the input values and you let the solver handle it. You can see a list of attributes which are recognized if you open the help window. We're going to go over a few of these later. So in the search, I'm going to type particle attributes, and I'm going to go here to attributes in particles. So here you can see a list of attributes which are recognized by the solver. So you have things like age and life and ID, for example. So age is the second since the particle was born. Then in linear physics, we have the force, which I just explained. That's the same as acceleration. We have mass, which we're going to be using. We have drag, air resistance. Then we have things for angular physics, such as orient, W, which is angular velocity, which we're going to have a look at in a few minutes. And then we have for the state, so we can have a particle die or stopped or be stuck. And then we have same for collision. So all these attributes, if you create them, they're going to have an effect on your simulation. So it's worth it to go and read over this once just to know what are the options out there. Some of them are really useful. We're going to have a look at what are the main ones, the ones you'll be using 99% of the time. So let's start with the most important one, our velocity. Right now, if we play our simulation, you'll see nothing is happening. And that is because our particles don't have any velocity. And right now it's set to inherit velocity. And since there's none, basically the particles are just stuck there. We can change this, for example, to set initial velocity. And basically this allows us to add a velocity in a certain axis. So for example, we can add it in Y. And this is a variance. So this means that the velocity can be +1 or -1. Same here, it's going to be either 1 + 1 or -1. So this one's going to go from 0 to 2. And same with this one. So if we hit play, we'll see all our points going up. So now this looks very boring. We need to add some variation and make this look more interesting. But that's the basics of it. So that's how the pop network works. So now let's actually start building a nice velocity source so our particles look better. So let's say that we create in a point pop a velocity attribute, for example. And I'm going to bypass the delete. Actually, let's just look at, I just want to look at one of the impacts. So I'm just going to say bullet impact is equal to 1. This is points. Let's delete non-selected. Let's just deal with only one of them. We need another equal. No, bullet impact. Oops, sorry. Need to bypass the delete. Okay. So this is just one of the impact locations. So let's go here. And I'm going to call this set B for velocity. So for example, if we create a constant and set it to be a vector and give it a value of 1 in y, and we plug this into our output velocity. The way I like to visualize them is by creating here my own guide. So I'll go to marker and we'll call it B, B, and B, and it's going to be a vector. You can leave it that color, and I like to scale it by 0.2. That is the same, actually the normal is being scaled the same. So right now, that is our velocity. So to better understand velocity, we need to have a solid understanding of vectors. A vector is a vector quantity that has a direction as well as a magnitude. In math, a vector is simply a list of numbers. So for example, I'm going to go here, just visualize 0.0 and just the V attribute. So a list of numbers, in this case is 0, 1, and 0. So these numbers are referred to as scalars. So a scalar is just a technical term for an ordinary number. So it can be 0, can be 0.3, minus 2.5. Then the dimensions of the vector determines how many scalar numbers it has. So for example, right now we have 3 numbers. So we call this a vector 3. You can actually see here, if we export our own, it's going to tell us that we can create a vector 2. So that's going to have 2 floats, a vector with 3. We can even have a vector 4 with 4 of them. Okay, so that's the dimensions of the vector. And then each one of these numbers, you can see, it's called a component. So we have the x component, the y component, and the z component. Now let's go back to the concept that every vector has a direction as well as a magnitude. This is probably the most important thing you have to remember. The direction is the way the vector is pointing. In this way, it's going up in y, and the magnitude is how long this line is. So those are the 2 properties that vectors have. Another interesting thing about vectors is that they don't have a position. You can't ask where a vector is. For example, if I say take 3 steps forward, I'm not talking about a specific location. The direction is forward, and the magnitude or amount is 3, which is the distance you have to move. This is relative, in this case to yourself. It means take 3 steps forward from where you are, but it's not an absolute position. Another example is if I say I'm traveling northeast at 50 kilometers per hour. The direction is northeast and the magnitude is 50. The magnitude of the velocity is also called speed, and it's a scalar value. So 50 in this case is the speed I'm going at. Now, distance and speed aren't vectors. They are just scalar values describing quantities. If I say 3 meters, I have a magnitude, but there's no direction, so it's a scalar. The same applies to speed. 30 kilometers per hour, it's actually a scalar, since it doesn't have a direction. So the key to remember is that vectors have both direction and magnitude. So you have to be able to answer the questions where and how much. I like to think of vectors as an arrow, which point toward a direction and have a certain length. So this makes sense in our example of velocity. It has a direction and an amount, and it's relative. What about the position attribute? The position attribute describes a point, and a point and a vector are mathematically the same thing. You can see here we have p, x, y, and z, and b, x, y, and z, and it just has 3 values and 3 values. So even though they are the exact same thing, we use them as different concepts. So a point represents a location, and it's always relative to the origin. So in this case, if I turn on our grid, when we say here, I'm going to turn off the velocity. when we say create a point in 7, 0, and minus 0.7, we're actually saying a direction from the origin. So we're saying move 7 units in X, so it's over there. Move 0.02 in Y, so that means up. And then in C, move minus 0.7. And we end up there. So I like to think of points as dots and vectors as arrows. Houdini will interpret the P attribute as a point. So you can actually see it's creating a point in this location, right? Or a dot. And then any other vector is going to be treated as a vector, not a point. So we can see right now it's drawing a vector, not from the origin, it's drawing it relative to that point. In Houdini, we can get the direction of a vector using the normalized bob, and we can get the magnitude using the length. You can use these two to separate a vector, and you can join them together by multiplying them together. Now, technically, the normalized node is just creating a vector that has a length of 1. So this is called a unit vector, and it just means any vector that has a magnitude of 1. Okay, so with that knowledge, we're now ready to create our velocity. So I'm going to actually rename this. And the way I like to work is, first, I like to create the direction and then the magnitude. So let's set this to set velocity direction. Okay, and let's say that our bullet is going to be hitting here in the center. I kind of want all this to be, it will look kind of like a splash of water. So I want the center part to go up, and the further away it is from the center, I want the vectors to go outwards. So in order to do that, we actually have to figure out where is the center, and we need to figure out also the distance. So let's actually do that. Actually, I'm going to move this now. Remember, we want to deal with our effect. While it's not time dependent, making it time dependent will be the very last thing. And this is our small visualizer just to see one of them. We can then turn it off to see all the others, but for now this is fine. And let's see. Let's add over here. Let's find the distance of all of these points. Basically the distance of all these impacts. We can actually get we can use extract centroid. This is a really cool node. So you can tell it that you want to run over pieces, and in this case it's a point, and you can give it a piece attribute, which will be our bullet impact. And we can tell it, right now it's going to output points. We can tell it to output an attribute, and basically it's going to create a centroid attribute. And what we can do now is we can measure the distance from every point to its centroid. And then we're going to fit that between 0 and 1, and we're going to get a sort of normalized distance. So for that, we need to do a for loop. So I'm going to do a for loop, so for each point. And I want to run over every bullet impact. Okay, so if we look at this, we're only looking at one impact at a time. So let's go into a point bob, and let's measure the distance. So we'll say distance between the position, and we're going to bind our centroid, which is a vector, and then let's export it as dist. Okay, and we can also visualize it in the color. And let's see, right now the distance is too small, so it's going to be mostly black, but let's see, let's call this get distance. Now what I would like to do is to measure what's the minimum and the maximum distance, and then we're going to fit it. So we will say distance from point to detail. We want the maximum, and we'll call it max dist. Let's not delete the original. Let's copy and paste it, and this one will get the minimum, and this will be our min dist. Now let's make another point bob. Let's connect it here, and we'll call this fit distance 0 to 1. So here I want to bind our distance, and we're going to fit it. And we're going to read our detail attributes. So we'll say it's a float from the first input. It's called min dist. So that's our source minimum. And then our source maximum is max dist. And actually I forgot to change the attribute class. That should be a detail for both of them. Okay, and now we're going to export it back to distance. We're going to overwrite it. Now we should see, if we look at it, we get values that go from 0 to 1. Okay, that's correct. And we can visualize the color. And now we should see that it goes from black to white. If we look at the for each, it should have done the same for all the other impacts. Okay, so now we have our distance to the impact. And we also have our centroid. So we can start creating a vector out of that to get our outwards direction. So let's go back to our set velocity direction. And let's visualize the velocity. So let's see, we're going to start with our up velocity. So we definitely want everything to go up. So I'm going to call this, just so we know, our up. So that's one direction. Now I want to create an outwards direction. And the way we can do that is by subtracting. So if we subtract our position from our centroid, which is a vector, and we normalize it. Again, I only care about the direction. So everything that I'm doing here, I'm going to be normalizing. I don't have to normalize the up because since it's 1, this is going to have a length of 1. So it is a normalized vector. So let's see, that's our outwards velocity. So what I can create now is a mix. And this is going to do a linear interpolation between both of them. So let's create both of them. And again, normalize for the result. And let's visualize the result. And now if I change the bias, you can see it goes all the way from pointing up to all the way to pointing outwards. So in our case, I want to have the distance control that. So the further out it is, the more it's going to point outwards. So for that, I'm going to bind the distance. And let's have a ramp. It's going to be a spline ramp, and I'm going to call it our up and outwards ramp. And we can fit this between 0 and 1. And in this case, this is going to be our min outwards. So min outwards direction. And this will be our max outwards direction. Okay, and this is now going to go into our bias. So let's see, let's go back out. And now we can see, if we move this ramp, we can control, based on the distance, how these velocities are affected. So let's see, I want the minimum outwards direction to be 0. So if we're 0, it means we're pointing up. And then our maximum is the one that I'm interested in changing. I don't want everything to point outwards completely like that, like flat. I would say maybe something like that. And then for our curve, I would say I want almost everything, most of the points pointing outwards, and just the ones at the center pointing directly up. So all right, this is looking better than what we had before, but it's still not very interesting. We need to add variation. And the best way to add variation here is to create some noise. So I'm going to create an anti-alias flow noise. And let's connect the position. Here we go. And I'm going to promote the frequency, the offset, and the roughness. And I'm going to set this to be a 3D noise. And then we're going to normalize this because we only care about the direction. And now let's look at our new vector. Okay, let's go back out. Let's increase the frequency. So I don't want it to be completely in any direction. I only want the noise to be going upwards. So we can create a cross product, and we can cross this up with our up vector, in this case 0, 1, 0, and then we can do another cross product like that, and this result is going to make sure that they're only pointing upwards in the positive direction. And again, let's normalize this like that, and we can now create another mix. So in this case, we're going to mix the result of the previous mix with our noise. We will normalize it once more. Okay, and again, we can use the distance maybe to control this. So we can create another ramp over here. So ramp, it's going to be a spline ramp, and this is going to be our dist noise ramp. And again, we can fit it. And we're going to have our minimum noise, which will probably be 0, and then our maximum noise. So max noise. And this is going to go into the bias in here. Now let's go up and let's start dialing this in. I'm going to change the noise amount to 1, and that is, I want to get the frequency right first of all. So let's see, how much noise are we actually, like how frequent this is going to be. And I'm going to start playing with the offset. Let's say I'm going to add a tiny bit more and add a bit less roughness. So something like this might work. So we can see we have like one general direction going there, another one there. We don't want it to be too high frequency that we can't tell the directions apart. But I think this will work. And then we can change our minimum noise back to 0 for the beginning. And then let's see how much is the maximum noise that we want. And then we can increase this one as well. And again, we can have more noise in the outward section. I mean the outer points, the ones that are further away from the impact. Okay, and this is starting to look more interesting. We have the direction set, right? They're going outwards. What we're missing to do now is set the amplitude. Let's go ahead and create another point pop. Let's add it over here, and I'm going to call this set b amp for amplitude. Or you can also call it magnitude. It's all the same really, it's just the length of the vector. All right, and the first thing I want to do is I want, based on the distance to the impact, I want the points that are closer to the impact to be longer, and the ones further away to have less amplitude or magnitude. So let's go ahead and let's bind our distance. And I'm going to create a ramp for it. And let's call it our distance ramp. And it's going to be a spline ramp. And then let's create a fit here. Let's call this our minimum speed. And let's call this our max speed. Okay, and then I'm going to multiply it. So remember, if we want to mix our direction, our normalized direction with magnitude, we can just multiply it. It's very important to always multiply the vector first and then the float. And you'll see by default it's set to 0. That's probably because our ramp over here just defaulted back to 0. So let's see. This right now is going to do the opposite. It's going to make the points further away. It's going to give them the biggest amount of magnitude. So I'm going to bring it down. And let's bring this one up. There we go. So let's flip it. And let's see, maybe we want to have some sort of fall off, and then same here. I don't want these points to have that much energy. Something like that. And let's say we don't want anything to have like a minimum speed of 0. Basically, we want everything to move. So let's just say 0.3. And then for our max speed, I want these points to shoot out a lot. Now here's a cool trick. If you want to see how far your particle is going to travel in one frame, you can change the visualizer guide. In this case, instead of 0.2, if you end up dividing, and I'll just do this here, let's just make any node like a box, and if I say 1 divided by 24, right, so if we divide 1 second by 24 frames, we get that value. So that's how much everything moves in a frame. So if we set this to 0.041, right, so this is how fast our particles are going to move in one frame. So in the next frame, they're going to be where the yellow arrow finishes. So let's see, maybe we want this impact to be way more, something like that. Should be pretty big. Okay, and again, we need to add some variation to this. So let's go ahead and create some anti-alias noise. So I'm going to connect the position. This time we want one-dimensional noise. And let's promote everything. And this time I'm going to fit it from, let's say, minus 0.5. Because we want to grab those negative values and we want to make it positive. We don't want anything. We don't want to be multiplying with negative values, because if not, we're going to flip the direction. And we don't want any of them going down. So let's see, let's move this down here. What we can do now is we can have a mix. And we can mix our distance, and we can also mix our noise in here. And I'm going to call it our noise amount. So let's start dialing this in. So let's see, let's set our noise amount to be 1. And let's see, I'm going to keep increasing our frequency until we start getting, I want to basically see some breakup. So let's see, now we start to see, right? We start to see some shapes. We don't want everything to be completely uniform. Maybe something like that. And then let's see the amplitude. So that's going to, you can think of that like as a contrast. So we have some very short ones, some very long ones. And let's see, we can add more roughness if we want even more variation. I think something like that is going to work. Okay, now we can dial our noise back down. And let's see, so how much do we actually want? We don't want like a crazy amount. I would say something like this might work. So you can see now our source is looking a lot more interesting. It's all going in different directions. Also, every particle has a different length. But there's one more thing we can add, and that is, if we look at the bigger picture, right? If we look at all of this, you will see that between all of them, they all have the exact same size. So again, we want to have some of them be very big, and we also want others to be small. So if it's a small impact, we want the velocity to be a lot less. So something we can do for that is we can use our bullet impact. So let's bring it in as an integer, and we can convert it to a float. So integer to float, and we can get a random value. I'm going to turn off clamp position to integer. Okay, and then we can have a ramp again to distribute how many of them will be high velocity and how many of them will be low velocity, and we'll call this our random amplitude distribution. Finally, let's fit it, and I'm going to call this our mean rand multiplier and our mean rand mult, and same for maximum. Okay, and we're just going to multiply this. We'll add it together. Oops, let's go back. Let's move this, and let's add this into the multiply. Okay, let's go back up. So the idea of this is to just multiply some of these chunks. So we want some of them to stay the same, or we can choose to, for example, if we leave it at 1, the smallest one will stay that size. But if we go like this, if we increase the second one, some of them are going to be very high velocity. So in our case, I think we can add just maybe 25% less in this case, and then let's see, we can go to maybe 1.7. And as far as the distribution goes, I want a lot of them to be very low velocity, and just a few of them to be very high velocity. So we can change this later on. Let's see, maybe let's go to 2. Let's see what it looks like from the camera view. Okay, so we're getting a pretty interesting distribution. Let's see, let's show all the other objects. Great, I think we're ready to actually go into simulation and to have a look at what this looks like. So I'm going to turn this off. I'm going to enable back our delete node, and let's go into the pop net. And there's one more thing we need, and that is just gravity. So I'm going to add a pop force. That's a very easy way of adding gravity, and I just want gravity in the negative y axis, and that's going to be minus 9.8. Okay, and I think we changed, yeah, so I need to make sure that we use the inherited velocity. There we go. Cool, and you can see some of these points are falling, and that's because we don't have a ground to collide it with. So let's start talking a bit about ground collisions. The easiest way to add a ground plane, just for collision, is to here go ahead and add a ground plane, and we have to merge it. Let's merge these two and have our output. You'll see it will create, this is actually creating an infinite ground. Even though it looks small, this is just a visual representation for it. It extends throughout the whole, basically it goes until infinite. But in our case, so actually if we hit play, we'll see that it works. Cool, so that's looking nice. Now this isn't our actual ground, we have our own ground. So how do we go about importing that? So instead of using the ground plane, I'm going to create a terrain object, and that's what we're going to use in here as our ground. So for that, we need to import our ground. So let's go back to our environment. There is our road. So there's many ways of dealing with collisions in DOPs, and every solver has its own way. Some use convex or concave geometry, others use just polygons, but the vast majority of them use SDFs. Particles only use SDFs, so that's very important to remember. We were going to go over some techniques for creating colliders for pops later, when we use the cars as colliders, but for this shot, we only need the ground. The nice thing about the terrain object is that it's going to detect that we're using the pop solver, and it's going to create an SDF representation of our terrain. Be aware that this is happening under the hood. So far for us, if we have a look at the viewport, everything looks okay. But if there's one word of advice I can give you, is whenever you're dealing with collisions, never trust the viewport. 99% of the times you will be looking at just a nice display, but it's not actually what the solver is using. You always want to make sure that you visualize the collision geometry itself. So for that, I'm going to select the terrain object, and I'm going to go down to collisions. And now you'll see by default it says use volume-based collisions. And I mean, there's a couple of tabs. I just know that the pop solver is going to use volume-based collisions, so that's the SDF. So you want to stick here to the RBD solver and the volume. And now you can enable the collision guide, and you can hide the guide geometry. And you can actually see there's nothing. Most likely it's because you don't have enough uniform divisions in here. You need to increase this, say to 100. And there we go. Now it's starting to give us a result. But if you show the guide geometry, you'll see this has so many small bumps and it's so fine. We aren't getting any of that in here. So again, let's keep increasing it, maybe 250. It's even more, maybe 500. It's going to take a while, but this isn't time dependent. It only has to cook once. Okay, let's have a look now. I think this is now probably a lot more accurate. Let's see, let's display our display geometry. And this is starting to look, yeah, way more accurate. I think that's good enough for now. I'm not going to go any higher. We can hide it now. Whenever you have issues with collisions in DOPs, it usually is because of the collision being too low res or it not being represented properly. So always keep an eye out for that. It will save you a lot of debugging time. Whenever something doesn't look right in a sim, the first thing I check is the collision geometry. Right, so let's hit play now. And we can see our particles are sliding a lot, and that's because by default the pop object has the friction set to 0, so we can increase that to 1. That's going to make them stop sliding so much. So it's just going to calculate our SDF in one frame. There we go. There's another thing I'd like to change, and that is sometimes particles, I think, yeah, you can see here our particles aren't settling correctly. And that's because we have our p-scale in here. So you know how the pop solver recognizes some attributes where p-scale is one of them. And we only need that when we are dealing with, basically when we're instancing the circles. We don't need it anymore. So let's make sure we remove it. It's very important that you clean up your attributes right before you go into a popnet. Just because there's so many of them that might be recognized by the pop solver. And as you can see in that case, it was giving us a wrong result. If we try it again. There we go. So let's go back to the shot cam. And let's see, let's look at this with the car. And we can do a top import. And that is going to import our points from the popnet back into subs. So for that, actually, I'm going to change this. Let's call it debris. This is our object that's holding the particles. So in our dop import, we'll tell it we want to import from the dop network. I want the debris. And I'm going to fetch geometry from dop network. Okay, and let's hit play. Okay, and there's a few things to tweak, but first of all, let's get rid of the color. Actually, let's do a attribute delete. I think it's a bit confusing. There we go. And I think for being bullet hits, these are going up way too high. So let's actually go to our magnitude. Let's bring this down to maybe 1.25, or let's say 1.5. And same for our, where is it? Max speed, let's set that to maybe 4.5. Okay, let's go back. Let's play again. Okay, that one's looking a lot better. There's still a few things to tweak, but I feel we're going in the right direction. So in the next lesson, we're going to finish up this effect, and we're going to be having a look at how to fix, for example, all the bouncing particles. We're going to add friction, and we're going to keep adding even more variation, and we're going to start fine-tuning our parameters just to get a nicer look out of it.